Okay, let's have another think about Denavit-Hartenberg with a slightly different take on it, just to make it very clear what we mean. So, like I said, Denavit-Hartenberg breaks down calculating homogeneous transformations in terms of two screw transformations, basically. And a screw transformation basically consists of a rotation around an axis and then a shift along the same axis, right? So you're moving something round, first of all, in terms of the angle here, theta, and then you're moving it along, in this case, by a distance d. Now, in this particular case, it doesn't matter which we do first. Most of the time, we can't just switch displacements and rotations, but because these things are a special case, it actually turns out it doesn't matter which way round you do them. So you can do rotation, then translation, translation, or rotation. You end up with the same result. So let's think about x-axis screw transformation. We're going to have a rotation around the x-axis and then along the x-axis. Right, so first of all, we're going to rotate by alpha, and then we're going to translate along x by a. Right, so this is basically the alpha, if you recall, is the thing that aligns the z-axes in our system. So we want to be able to say, yeah, we want to move the next. Well, we want to know what's the translation, what's the rotation which takes the z-axis in the next section back to what we had to start with. So we've got this alpha basically between them. So we need to work out what that transformation is. And like I said, it's just going to be rotation around x. And then we've got to move them to align them. So we then move along x by the distance between them, which is a. Right. So that's quite easy. So first of all, what we say is, let's calculate the rotation around x by alpha, right? So it's rotation around x, so x stays the same, and then we've got here's the 3x3 component in this homogeneous transformation, which will give us our rotation around x by alpha I in this case. Then we've got the translation that we want. So we want to translate now along x, right, by I. So I is obviously going to be the frame. So that homogeneous transformation matrix is also quite simple. We've got the 1, 1, 1 from the identity rotation component, which is nothing, and then we've got the translation component going in there. So we can basically multiply those out. Rotation, then translation. In fact, you could just put them straight in if you'd rather do that. This is just, again, doing things a little bit from first principles, but basically just demonstrating you can multiply that with that, and we end up with a representation of this transformation, which is quite simple. It's just got this rotation part and the the rotation part and the translation part there. We can easily do another screw transformation, which is the second one we're going to need when we're actually doing Denavit-Hartenberg, and that is going to be rotation around z and then along z, right? So this time it's going to be the rotation basically to align the x-axes. In fact, that's what the theta is going to be for, and then you've got the translation up and down by how high up or further down the other joint was in the sense of the z-axis, right? So that's quite easy to understand. So here we go, looking at terms. We have a rotation matrix then around z by theta I, and then we've got a translation along z by di, right? So rotation around z, this is then homogeneous format. The z element stays the same, so there's a 1 down there, and we've got the appropriate remainder of this 3x3 rotation matrix. No translation element there, but we've also got then a translation in z of di. So again, we can multiply those together. We could just put them straight in. It would give us the same result. Here is then the rotation element around z, and here's the displacement along z, right? So we've got our 4 parameters, and we've got 2 parts that we've now built together. So what we're going to do is we're first going to do the x-axis screw transformation there. And then we're going to do the z-axis screw transformation. Just go back to say that again. So aligning here, right? We're going to align here, align the z-axis by rotating by alpha around the x-axis, and then shifting along the x-axis to get the z-axis to be coincident. And then what we do is we then deal with what's happening at the other joint end, and we basically want to deal with the shift up and down, right? The shift up and down the z-axis, and also the rotation around the z-axis such that we align the x-axis, right? And this is generally then the theta 1 is going to be, theta I is going to be the control variable, right? So we've got those two things that we've got to work out. We've already got these from before, right? We've got the rotation part around x, translation along x, rotation around z, translation along z. We've already calculated those values from before. And then what we do is we multiply them together and get the overall matrix, which is the homogeneous transformation matrix between two frames, where the parameters are in terms of alpha, theta, A and D, right? And when we're doing this transformation matrices and you end up with your homogeneous transformation, always remember, because of the form of a homogeneous transformation matrix, we've got this upper 3x3 part, which represents rotation. We've got this 3x1 part, which represents translation. We can just look at the matrix like that, right? And we can immediately say what the corresponding endpoint is. So it's always, like I said, it's always a good thing to do that, so you can check things every step of that you go in. So let's just have a last go through of the 4 Denavit-Hartenberg rules. The classical rules are, again, for a revolute system, and most of them are that we're looking into, the z-axis is placed along the joint of rotation, right? So that's the very first fundamental thing we've got to remember. And if it's prismatic, that means it's moving in and out, it's sliding in and out. That's going to have to be the z-axis. The x-axis has got to be perpendicular with the z-axes, the current one and the one before. The y-axis is then put in by using the right-hand rule, right? Because we want to make sure we get it all right. And the x-axis has got to intersect the past z-axis. Otherwise, you can't approximate these things using these two screw transformations, right? So z-axis is placed along the direction of the first rotation joint. That's the first joint that we've put in here, right? That's the first axis, z I minus 1. Here we put in the next one. This is zi, right? And the rotation between them gives us the alignment. We see that the z-axis, sorry, the x-axis is perpendicular. This is the z-axis has got to be perpendicular to this previous z-axis, so this is going to be 90 degrees. And it's also got to be perpendicular with the next z-axis as well. So there's got to be perpendicular here. It's got to be perpendicular here. We put in the y by just using the right-hand rule, because if you've got two axes, that means you've got no alternative but to put the third one in the place it's got to be. So it obeys the rule in both conditions, in both ones, the ones at I and I plus 1. And x, so basically the x-axis has got to intersect the previous z-axis, because we don't forget we're moving along axes. We move along x and we rotate along x, and we move along z and we rotate along z. So these things have got to have certain properties.